Hello everyone and welcome back to the channel. I'm your host and this is AITTL, the place where we break down complex computer science topics to make you a better engineer. This is next video in our flagship data structure and algorithm series. Today we are going to completely fundamental. We're talking about mastering the assembly line, or as it's formally known, array traversal. As you can see from our whiteboard, we have two figures looking at a long line of data. This is the core of so many programming challenges. Understanding how to efficiently walk through the data is absolutely first step in solving complex engineering problems. Whether you're a beginner or a seasoned pro, these patterns are your bread and butter. So, if you're ready to level up your problem solving skills, you're in the right place. Let's get into it. To start with, let's use a simple but powerful analogy. The array is a conveyor belt. Imagine you are an inspector in a factory. The items on the belt are your data and they are stored sequentially, one after another in a predictable order. A key property of arrays is that if you have constant time or O1 access, this means that you can instantly look at any item on the belt just by knowing its position or index. But here's the catch. As your inspector says, I can only inspect where I'm standing. You can't see the whole belt at once. You are at a single position. This means we need a strategy to move the inspector along the belt to process all the items. This strategy is called traversal, and how we choose to do it can make or break our algorithm efficiency. The standard inspection. The first and most common strategy is what I call as the standard inspection. This is your basic for loop and the first thing we all learn. As we are showing it here, we start at index 0, inspect the item, move to index 1, inspect that item, and so on until we reach the end. The code is simple for I in range length of array. Let's do a quick analysis. The behavior is a straightforward left to right traversal. The time complexity is O of n because if the array has n items, we have to perform n inspections. The space complexity is O of 1, which is fantastic because we aren't using any extra memory beside the loop variable I. This simple pattern is the workhorse for so many common tasks. If you need to find the maximum value in the array or perform a simple linear search to find an element, this is the tool you'll use. But when one direction isn't enough. But what happens when moving in just one direction isn't enough to solve the problem? Let's consider a classic interview question, checking if a word is a palindrome. A palindrome is a word that reads the same forwards and backwards like a race car. To verify this, our inspector at the beginning needs to know what is at the very end. The character at the start must be compared with the character at the end. A simple forward moving loop can do this easily. Now, a beginner's first instinct might be to make a reverse copy of the array and then compare the two. While this works, it's a trap. As you can see at the bottom, creating that wasteful copy has a hidden cost. You're using O of n extra memory. For a massive array, this is incredibly inefficient. We need a smarter way to solve this without using more space. Before we solve the palindrome problem, let's introduce another essential pattern, walking backwards. Sometimes the most intuitive way to solve a problem is to start at the end and move towards the beginning. The syntax for this is straightforward in Python. It's a range len of array minus 1, comma minus 1, comma minus 1. We start at the last index and our loop stops after it processes index 0. But why would we do this? Because sometimes the answer for the element at your current location depends on the future. That is, the elements that come after it. A great example is daily temperatures problem. To find out how many days you have to wait for a warmer temperature, it's much easier if you start from the end. By walking backwards, you've already processed the future days and you can use that information to make a quick decision for the current day. It's a powerful way of thinking. Okay, so we know going forward, we know going backward, but what about our palindrome problem? This is where we see the in-place revolution, a beautiful and efficient pattern that uses two inspections instead of one. Instead of creating a second conveyor belt, which is a wasteful copy, we just have one inspector start at the beginning, the blue one, and a second inspector start at the end, the red figure. Their job is to swap the items they are looking at. After the swap, they both take one step inward and repeat the process. This is the core idea of two-pointer technique. We operate directly on the original array, which we call as in-place operation. Look at the efficiency gains. The time is still O of n because we touch each element roughly once, but our space complexity is now O of 1. We have eliminated the need for that costly extra memory. Converging from both ends. Let's formalize this powerful pattern. We call this converging from both ends. Instead of a one lone inspector, we now have a coordinated team. We initialize a left pointer at index 0 and a right pointer at the last index, which is n minus 1. Our main logic runs inside a while loop with a condition while left is less than right. This ensures they don't cross over. Inside the loop, the process is always the same. Make a decision based on the value at array of left and array of right. This could be comparison, a swap, or a calculation. Move the pointers. Based on the decision, you'll increment left, decrement right, or maybe both. This simple, elegant structure is the foundation for solving a huge class of array-based problem efficiently. The logic of sorted data. The converging two-pointer technique became a superpower when you are working with the sorted data. The sorted property allows you to make intelligent, greedy decisions. Let's take the famous two-sum problem on a sorted array. Our target is 14. We start with our left pointer at 2 and our right pointer at 10. We calculate the sum. 2 plus 10 equals 12. Now we make a decision. The sum 12 is too small. Since the array is sorted, we how can we get a bigger number? We know that the everything to the left of our left pointer is smaller. So moving it backward won't help. Our only hope for a bigger sum is to move the left pointer forward. So our left pointer moves to 4. The new sum is 4 plus 10 equals 14. Wow, we have found a target. The logic is simple and powerful. If the sum is less than the target, you need a bigger number, so you move the left pointer right. If the sum is greater than the target, you need a smaller number, so you move the right pointer to the left side. Let's bring it all together and solve our original palindrome problem using this new technique. Here's a flowchart of the two-pointer logic for race car. We start with left at R and right at the final R. The first step inside the loop is the decision. Is array left equals array right? Yes. R equals R. Since they match, we execute the yes branch. We move our pointers inward by incrementing left and decrementing right. We then check our loop condition. Is left greater than equals right? No, they haven't crossed yet. So we loop again. Now left is at A and the right is at A. They match. Move pointers. The loop continues this way. If at any point the characters do not match, we would immediately follow the no path and return false. If the loop completes without finding any mismatches, meaning the pointers have crossed, we exit the loop and return true. It's a verified palindrome solved in O of n time and O of 1 space. Optimization. This two-pointer pattern isn't just for verification problem. It's also a powerhouse for optimization problem, like the classic container with most water. The goal is to find two walls that can hold the most water. The area is calculated by the width between the walls times the height of the shorter of the two walls. We start with the pointers at the widest possible positions. The height of the water is limited by the shorter wall. In this case, the one with height equals 3. The left wall says, I am the bottleneck. Now, we have a choice. Which pointer do we move? This is the greedy logic. If we move the tall wall inward, our width shrinks, but the height is still limited by the short wall. The area can only get smaller. Therefore, our only hope of finding a larger area is to get rid of the current bottleneck. We must move the pointer to the short wall inward, hoping to find a taller wall that will give us a better area. Why do we obsess over traversal? At this point, you might be thinking, this is clever, but does it really matter that much? The answer is resounding yes. The reason we obsess over traversal strategy is performance. Look at this graph. The red line represents a brute force solution, usually involving nested loops, which has a time complexity of O of n square. The green line is a smart traversal pattern like the two-pointer strategy, which is O of n. For smaller inputs, they look similar, but as the input size grows, the O of n square solution runtime explodes exponentially. But let's put some numbers on this. For an array with 10,000 items, a brute force O of n square approach would take roughly 100 million operations. This could take a minute to run. The O of n two-pointer strategy would take about 10,000 operations, which would finish in milliseconds. This is the difference between an application that feels snappy and one that feels broken. This is why we obsess over traversal. The truly beautiful things about these patterns is that they're not just isolated tricks. They are building blocks that you can combine to solve even harder problems like the infamous threesome. The goal is to find three numbers in an array that sums to 0. The brute force solution would use three nested loops, which is O of n cubed. Terrible. Here is the elegant combined approach. First, sort the array. This is the key that enables our smart logic. Next, iterate through the array with a standard for loop. We'll use this outer loop to fix one number, which we'll call as the R anchor. For each anchor, we then run our two-pointer technique on the rest of the array to the right of it. The goal for the two pointers is to find two numbers that sum up to the negative value of our anchor. By combining a standard loop with a two-pointer pattern, we reduce the complexity from O of n cubed down to O of n square, a massive improvement. Now the engineer decision matrix. So with all these patterns, how do you know which one to choose? Here is an engineer's decision matrix to help guide your thinking. Start by asking, what is the goal of the problem? Is it to simply process every item sequentially, like finding a sum or a maximum? If so, standard forward iteration is your best bet. Second, does the answer at your current position depend on the data that comes after it or the future? This is a strong signal to the reverse traversal. Third, is the array sorted or can it be sorted? Are you looking for pair, triplets, or trying to optimize something based on two endpoints? This is the prime use case for two-pointer technique. This mental flowchart will help you quickly identify the most efficient traversal strategy for the problem at hand. Now let's debugging your logic. As powerful as these patterns are, they come with a few common pitfalls or gotchas that can trip you up. Let's talk about debugging your logic. First, off by one errors. These are classic. Double check your loop ranges. Are you supposed to go to n or n minus 1? This is a frequent source of bugs. Second, infinite loops. Specifically in the while left less than equal less than right pattern. You must ensure that inside the loop, you're always either incrementing left or decrementing right in every possible code path. If you forget to move them, your loop will continue to run forever. Finally, always consider edge cases. What happens if your function receives an empty array? What about an array with just one element? Test these cases explicitly. A robust algorithm handles all valid inputs, not just the happy path. Traversal is a design choice. So let's bring it all home. The main takeaway from this video is that traversal is a design choice. We have covered three main strategies: simple forward iteration, reverse traversal for when you need to see the future, and the powerful two-pointer technique for in-place efficient solutions. Don't just loop blindly. When you approach a new problem, take a moment to look at the data structure, look at the constraints, and consciously choose the inspection strategy that best fits your goal. This deliberate choice is what separates a good programmer from a great engineer. And that's a wrap for our deep dive on array traversal patterns. I really hope this gives you a solid framework for your problem solving. This was another episode in our DSA series here on CSAI TTL. If this video helped you, please do me a favor and hit that like button, subscribe to the channel, and make sure you click that notification bell so you don't miss out on the next video. Be sure to explore CSAI TTL channel for your other content on algorithm and interview preparation. Finally, I want to hear from you. What topic should I cover next? Drop your suggestions in the comments below. Thanks for watching, and I'll see you in the next one.